Okay, the last three exercises in the derivative set deal with interpreting the derivative and motion graphs and interpreting the motion. So, I'm just going to do some example problems from those. Interpreting the meaning of the derivative. So the meaning of the derivative is just rate of change. It's the instantaneous slope. It's not the average, it's not over an interval, this is how the function is changing at this point. So that's what we need to find. And here we have the function c gives the cost in dollars of producing X liters of a certain sauce. Okay. The slope of the line tangent to the graph of c at x equals 12 is equal to 4. All right. That's a really roundabout way of telling us that c prime at 12 is 4. Okay. So the rate of change of the cost when producing 12 liters of sauce is equal to $4 per liter. That's what we need to do. So at time when 12 liters of sauce is produced, the costs are increased by $4 per liter. When the amount of sauce produced is 12 liters, the cost increase at a rate of $4 per liter. This one is better. It's $4 per liter. That's a rate of change. Cost increased by $4 is just constant. That's a measurement. It's not a rate of change. We have to match that rate of change, so it's $4 per liter. The cost of producing the sauce increased at a rate of $4 per 12 liters. That's not what this says at all. It's telling us that the rate of change of producing 12 liters of sauce is $4 per 1 liter. So in this case, we're going to go with B. I don't even need to C. D. Yeah. Here, interpreting motion graphs. So we have to pay very special attention to what our units are and how they are, or what they're telling us about the graph. But an object is moving along a line. The following graphs gives the object's velocity over time. For each point on the graph, what's known as the object moving forwards or backwards. So we have an object moving over a line from start to finish. He can be moving to the right or to the left. Positive and negative are indicators of directionality. So if he is moving forward, his velocity is positive. If he is moving backwards, his velocity negative, and that he is moving in this direction, but towards the left or backwards. So here, where our velocity is at 4, he's moving forwards. Here, where our velocity is 1, he's still moving forward, granted at a slower pace, so he is slowing down that negative slope, but he's moving forwards. And then both of these are negative velocities. Moving backwards at 2 whatever meters per second. Here he's moving backwards at 3 meters per second. So we have to interpret what that means. There we go. So the next one. An object is moving along a line. The following graph gives the object's position relative to its starting point over time. For each point of the graph, is the object moving forwards, backwards, or neither? So now we have the position. If position is positive, he is moving away from the object. If the position is negative, he is moving towards, so again, forwards and backwards. So let's see. At time, here. His position is at somewhere between -4 and -5. But the slope here is taking him towards that 0. So his position is getting closer to it. Velocity is increasing. He is moving forwards. I hate these interpretation ones. So let's diagram this out. Here's where you started. This would be position is positive, position is negative. Then we also want to look at the velocity, how he's moving. So for these, his position is negative, but it's decreasing. It's not his velocity. I'm going to say he's moving forward. And the thing that's throwing me is I think that all of these are moving forward. Now he started at -5 and he is increasing his position all the way through. Even here, even though his position is at 0, his slope, his velocity is increasing. So he's moving this way. He's moving forward, I think, through this whole graph. Because we can see, for this entire thing, his position is always increasing. At each point that we measure, his position is increasing. You started back here, -5 meters away from 0, starting point, and then increasing. I think it's moving forward the whole way. Let's see. Okay. Now, I was a little uneasy because, again, it's like when you bubble 3 answers on a test, and the next one is also that answer. It's like 3 C's in a row, and you get another C. Like, you want to think about it. You want to go back and check your conditions. But in that case, it was. What was that? All right. Here's a fun graph. I want to get to one of the speeding up, slowing down ones. I think this is it. Yes. Okay. Because this has 2 criteria associated with it. But let's see what it's describing first. An object is moving along a line. The following graph gives the object's velocity. So how fast it's traveling. For each point on the graph, the object speeding up, slowing down, or neither. That is acceleration. So we're given the velocity graph, but we need to read the acceleration. That's its derivative. So now we've got 2 things going on. First, we have to figure out the direction of travel. That's velocity. Is it going forwards or backwards? So velocity is negative, backwards, velocity is positive, forwards. And then we have to look at the acceleration. How is the velocity changing to get that speeding up or slowing down? If the acceleration is in the same direction, then they're speeding up. If the acceleration is in the opposite direction, then they're slowing down. So let's find the velocity for all of these. Velocity is negative, so he's going that way, that way. Velocity there is constant. The velocity here is positive, so he is going forward. Now, let's look at the acceleration. The acceleration is going to be the derivative of this velocity graph, so the slope. Here, my slope is negative. So at this point, the velocity is to the left and the acceleration is to the left. So that would be speeding up. They are moving backwards faster. But if we look here, the velocity is to the left, but our acceleration is positive. The slope is positive. So at this dot, we're going to have it slowing down. The acceleration is in the opposite direction of travel, so you're slowing down. Here, the velocity is 0, and our slope is negative. But if we have no velocity, we can't be speeding up or slowing down or neither. So for this one, I think it's going to be speeding up, actually. We have 0 velocity, so it doesn't matter which direction you go. It's going to be speeding up if we interpret that correctly. We would have the neither case if it was right at one of those vertices. Here, we are going to the right now. Our velocity is to the right, so positive velocity, but it is a negative acceleration, so we're braking, so we are slowing down. So I have to look at those two characteristics. One, what direction am I currently traveling, and how is that changing? Is it getting bigger in that direction? Is it getting smaller in that direction? So here, same direction, we're speeding up. Here, opposite directions, we're slowing down. Here, speeding up, because there was no initial direction, so any way we accelerate is speeding up. And here, we are slowing down because we have that opposite effect. Let's see. Check again. Oh, this one. So it's probably a neither, like I thought it was. Or I could interpret this as slowing down because it's a negative acceleration, or neither. But again, our initial velocity there is 0. Let's see, is it neither? They wanted neither. Okay. Again, I would expect it speeding up. Neither I can see because that initial velocity is 0, but okay. All right. Let's look at motion problems. Motion problems are talking about the motion of something and running through the derivatives. So we have a particle moves along the x-axis. The function gives the particle's position at any time greater than 0. What is the particle's acceleration? So the order that these go, we have position, velocity, and acceleration. And the way they are related is original function, first derivative, second derivative. And we can keep going. Third derivative is the rate of change of the acceleration. The fourth derivative is the rate of change of the rate of change of the acceleration. But these are the three big ones: position, velocity, and acceleration. We're talking about motion. So if we want to find the particle's acceleration, we need to find its second derivative. So we're going to take 7t minus 3. That's its position. We're going to take its derivative to get the velocity function, which would be 7. And then we're going to take the derivative of that to get its acceleration function, which would be 0. So its acceleration at time 6 is 0. Which makes sense. That's a linear function. Linear models have a constant slope, which means they're not changing, they're not accelerating as time progresses. They're just keeping that slope the same. So its acceleration is 0. All right, let's leave that up there, actually. Let's get rid of this. So this kind of combines a little bit of both of the last two exercises, because in this one we're going to have to interpret a direction of motion. Particle moves along the x-axis. Particle's moving time 0. What is the particle's velocity? So we have its position. We want its velocity at time 2. So we're going to take its derivative. Its velocity is the derivative of the position. So 6t squared minus 8t minus 8. And we want to find its velocity at time 2, so we're just going to plug in 2 to that. So 6 times 4 is 24, minus 16, minus 8, which is 0. It is stopped. What is the direction of the particle's motion at time equals 2? Well, its velocity is 0. It's not going anywhere. So we have to hope that there's another answer. Neither. Okay. So neither. It's not going anywhere. Its velocity is 0. It's stopped. We can look at its acceleration at time 2 as well to see what direction it might be accelerating, but I'm going to go stick with neither for this one. I think the Khan Academy did not want us to go that in depth. Let's see. Yes. Okay. This one does. Speeding up, slowing down. So again, we're going to have to look at the acceleration most likely, which is what they're calculating up there. So, cool. Particle moves along the x-axis. So here it's kind of working us through the entire problem. We want to find the velocity and the acceleration, and then we're going to answer whether it's speeding up or slowing down. So let's find our velocity function. If we have t squared minus 12t plus 30, our velocity function would be 2t minus 12. Our acceleration function would be the derivative of the velocity, which is 2. And then we can go through and answer these questions. Our velocity at 6 is 2 times 6, 12. Minus 12 is 0. So it's not moving anywhere. It is stopped. Its acceleration, what is the particle's acceleration at time 6? It's 2. So, is it speeding up, slowing down, or neither? In this case, we're going to have to go with neither because of our velocity. It is stopped, not going anywhere, so we can't be speeding up or slowing down until we actually have a direction of travel. So our answer would be neither, but we would look at its velocity, positive acceleration would be speeding up. Negative velocity, negative acceleration would be slowing down. Positive velocity, negative acceleration would be slowing down. Excuse me, a negative, if they're both the same sign, they're speeding up. If they're opposite signs, they're slowing down. Let's just put it that way. All right, and that is neither. Check again. What, did I miss a velocity? That's correct. Oh, I bet I dropped a negative. 2t minus 12 plus, yeah. Times 6. Oh, not giving me the position function, it's giving me the velocity. So these are not. Oops. All right. At least it's the last problem, right? tricking me by making me read. So they're giving us the velocity function. We want to find its velocity and acceleration, so these are going to be, its acceleration is going to be 0. Which is why it's not speeding up or slowing down. Its velocity at time 6 would be 36 minus 72, so it's negative 36 plus 30 is just negative 6. There we go. So it's traveling to the left, but it's not speeding up or slowing down, it's neither. There we go. Okay. All right, guys. It's interpretation, it's mostly concept. I know all of you are smart enough to do this. So take your time. And again, if you have the concept, if you kind of understand what's going on, you're in good shape. This is really just interpreting the derivative, making sure that you know it's a rate of change and that we use it to find rates of change and interpret motion and things of that nature. Yeah. Do your best. We'll see you next time.